Objective 3 of Section 2.7, Derivatives and Rates of Change. The student will know and use the definition of the derivative. We have seen that the same type of limit arises in finding the slope of a tangent line or the velocity of an object. The tangent problem is the same thing as the velocity of an object problem. Velocity of an object at an instant. In fact, limits of the form limit as h approaches 0 of f of a plus h minus f of a all over h arise whenever we calculate a rate of change at an instant in any of the sciences or engineering, such as the rate of reaction in chemistry or marginal cost in economics. Since this type of limit occurs so widely, it is given a special name and notation. So here's the big definition that you have to know, okay? The big definition that you have to know. The derivative of a function f at a number h, denoted by f prime of a, is f prime of a equals the limit as h goes to 0 of f of a plus h minus f of a all over h if this limit exists. Now, this h, remember, was x minus a, and the equivalent equation is that x is a plus h. If we write x equals a plus h, then we have x equals x minus a by subtracting a from both sides, and h approaches 0 if and only if x approaches a. No big news flash there. Therefore, an equivalent way of stating the definition of the derivative, as we saw in finding tangent lines, is f prime of a equals the limit as x approaches a of f of x minus f of a all over x minus a. And from here, it's really clear why we call either one of these things a difference quotient. Okay, so you often hear that sort of language. Difference quotient. Because you have a quotient, a division, you have a quotient, and top and bottom are both differences, subtractions. So difference quotient, they are both actually called the difference quotient. Now, this is without the limit, right? This by itself is a difference quotient, and goes back to Newton. Okay, so here's an example. How would we use this definition of the derivative? The derivative of the function, find the derivative of the function f of x equals a simple quadratic function. F of x equals x squared minus 8x plus 9 at the number a. Okay, so we're going to use the definition, and this is definition of a function at a number a. So f prime of a equals limit as h goes to 0 f of a plus h minus f of a all over h. Well, what is f? F is that quadratic function. And so f of anything is the square of that thing minus 8 times that thing plus 9. And that thing now is a plus h. That's the input. And so we're going to square it. We're going to subtract 8 times it. and add 9. And then from all that, we're going to subtract f of a, which is obviously a squared minus 8a plus 9. And it's all over h, and then we're going to let h go to 0. And it's going to get uglier before it gets prettier, but it will eventually get prettier. And so writing a plus ah times itself and foiling, we get the perfect square trinomial a squared plus 2ah plus h squared, and distributing a negative 8, we have negative 8a minus 8h. We got a 9. Then we'll distribute the negative, or negative 1 gets distributed. And we have negative a squared plus 8a minus 9. Well, you can see now how it's going to get prettier, because we're going to have cancellations, as we often do when we find the derivative, using the definition, when we find the derivative of a simple polynomial function. We get these nice cancellations, and most of the terms then are going to be gone. Okay, all that's left is 2ah plus h squared minus 8h, and of course h is a factor of all three of those terms in the numerator. And so because we can factor out h, 2a plus h minus 8 all over h, hack. It's just 2a plus h minus 8. Well, we're taking the limit as h goes to 0, so the h then just goes away. The 2a and the minus 8 are constants, and so the limits there are just the 2a and the negative h. And so that is your derivative, 2a minus 8. That's the derivative of the given function at the number a. So that's a problem that you have to be able to do. Find the derivative. It might have been at a certain number, but it was at a. We define the tangent line to the curve y equals f of x at the point P, which has coordinates a, f of a, to be the line that passes through P and has slope m. Since by definition 4 this is the same as the derivative f prime of a, we can now say the following. Okay, so we see f prime of a, and in our minds we're kind of hearing slope of the tangent at a, slope of tangent at the number a, the x value a. We can now say the following: the tangent line to y equals f of x at the point a, f of a, is the line through that point whose slope is equal to f prime of a, the derivative of f at a. If we use the point slope form of the equation of a line, okay, right, point slope form is y minus y1 equals m x minus x1. We can write an equation of the tangent line to the curve y equals f of x at the point a, f of a. So here's the same thing, right? This is y minus y1 equals m, slope of the tangent, x minus x1, right? Because x1, y1, that's the point A, f of A, and the slope of the tangent is f prime of A.